In this lecture, we'll answer two questions. On both questions, we'll find out the area of a shaded region. So we'll start with the first question. In the drawing, we have a big semicircle, a big quarter circle AOB. Quarter circle AOB contains of those two shapes. It contains this semicircle and this small quarter circle, and our task is to find out the area of this shaded region. We also know that AO is the radius of this big quarter circle, and it is equal to 10 units in its length. So BO is also the radius of this big quarter circle, and therefore it is equal to 10 units in its length. BO equals to 10. In the next step, we'll define the center of this semicircle. This point is point C. The diameter OB of this semicircle equals to 10, and therefore the radius must be equal to 10 over 2, that is 5. So the radius CO of this semicircle equals to 5 units in its length. Likewise, the radius CB of this semicircle also equals to 5 units in its length. AOB is a quarter circle, and therefore this is a right angle. Angle AOB is a right angle. Likewise, this is the small quarter circle, and therefore this angle is a right angle. We define the touching point of this small quarter circle with this big quarter circle. This point is point P. We define this point as point Q. We define this point as point S. We define the touching point of those two shapes. That is to say, of those this small quarter circle with this big semicircle. We define their touching point. This point is point M. So the big semicircle touches this small quarter circle externally at point M. And now you have an external match between two shapes. You can implement rule 10. Repeat quickly on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together passes for their touching points. In the drawing, we have those two circles that touch each other externally, and this point P. The center of this circle is at point O. The center of this circle is at point M. The straight line that connects the centers together is of course the straight line OM. And according to this rule 10, the straight line OM passes for point P, that is their touching point. Again, the straight line OM passes for their touching point, that is point P, or OPM is one straight line. Again, according to this rule 10, OPM is one straight line. So we can implement rule 10 in our drawing. In our drawing, those two shapes, that is to say this small quarter circle and this big semicircle, touch each other externally at point M. The center of this small quarter circle is at point Q. The center of this big semicircle is at point C. The straight line that connects the centers together is of course the straight line CQ. And the straight line CQ must pass for their touching point, that is point M. Or CMQ is one straight line. Again, CMQ is one straight line, according to rule 10. So we join point C and Q together by a straight line, and the straight line CQ must pass for point M, that is their touching point, according to rule 10. can see from the drawing that indeed the straight line CQ that connects the centers together passes through point M, that is the attaching point, exactly according to rule 10. And because of the fact that CMQ is one straight line, it means that CQ in total must be equal to CM plus MQ. So CQ equals to CM. CM is the radius of this semicircle that equals to 5. So CM equals to 5. Plus QM. QM is the radius of this small quarter circle. We define the radius of this small quarter circle as x. So QM equals to x. So in total, CQ, according to rule 10, CQ equals to CM plus MQ. That is to say, CQ in total equals to CM, that is 5, plus MQ, that is x. So in total, CQ equals to 5 plus x units in its length. So I did not, CQ equals to x plus 5. CQ equals to x plus 5 units in its length. In the next step, we will implement the Pandora's theorem on this right triangle, triangle COQ. So a copy triangle COQ in the new page, and we will implement on it the Pandora's theorem. Side CQ equals to 5 units in its length. It is the radius of this semicircle. The hypotenuse CQ equals to x plus 5 units in its length according to rule 10. Here by PT is the evaluation for Pandora's theorem. So actually, this is the right triangle COQ that the copy from the original drawing. In this right triangle COQ, according to the Pythagoras theorem, in any right triangle, the score of the hypotenuse equals to the sum of the scores of the perpendiculars. So in this right triangle COQ, CQ squared, that is the score of the hypotenuse, equals to CO squared plus OA squared. Again, CQ squared, that is the score of the hypotenuse, is equal to CO squared plus OQ squared. CQ squared, that is the score of the hypotenuse, is equal to CO squared plus QO squared. CQ is x plus 5, therefore CQ squared is x plus 5 squared, and is equals to CO squared. CO is 5, therefore CO squared is 5 squared, that is 25, plus QO squared. So in total, we should find out that x plus 5 squared equals to 25 plus QO squared. Here we will subtract 25 from this equation, equation 1. If I get it according to equation 1, x plus 5 squared minus 25 equals to q all squared. And again we shall find out that according to equation 1, q all squared is equal to x plus 5 squared minus 25. In the next step, we'll join points O and P together by a straight line. Point O is the center of the big quarter circle, point P is the point of the big quarter circle itself, therefore PO is the radius of this big quarter circle. According to what is given in the equation, the radius of this big quarter circle AOB equals to 10. So PO equals to 10, it is the radius of the quarter circle. PO equals to 10. So PQ or QP, point Q is the center of this small quarter circle, point P is the point on the small quarter circle itself, therefore QP is the radius of this quarter circle, of this small quarter circle, that equals to x according to our definition. So in the next step, I'll copy the right triangle PQO in a new page and we will implement the Pythagoras theorem on this right triangle PQO. Here by PT is abbreviation for Pythagoras theorem. The hypotenuse PO equals to 10 units in its length. It is the radius of the big quarter circle. So actually this is the right triangle PQO that I copied from the original drawing. This right triangle PQO, according to the Pythagoras theorem, PO squared, that is the square of the hypotenuse, equals to PQ squared plus QO squared. This will be equation 2. So PO squared, that is the square of the hypotenuse, is equal to PQ squared plus QO squared. PO is 10, therefore PO squared is 10 squared, that is 100. And it is equals to PQ squared. PQ is x, therefore PQ squared is x squared plus QO squared. QO is the missing side, so we leave it as it is. So in total, according to equation 2, we actually found out that (100) equals to x squared plus QO squared. Here we will subtract x squared from this equation, equation 2, and get that according to this equation, equation 2, 100 minus x squared equals to q all squared. So according to equation 2, we actually found out that q all squared is equal to 100 minus x squared. This is according to equation 2, and according to equation 1, we already found out that q all squared is equal to x plus 5 squared minus 25. So we have two different equations for q all squared. Therefore, we will create equation 3 that states that q all squared according to equation 1 must be equal to q all squared according to equation 2. Q all squared according to equation 1 equals to x plus 5 squared minus 25, and it must be equal to q all squared according to equation 2. Q all squared according to equation 2 is equal to 100 minus x squared. So in total, according to equation 3, we found out that x plus 5 squared minus 25 equals to 100 minus x squared. So here we will open the brackets of this expression, x plus 5 squared, and get that according to equation 3, x plus 5 squared equals to x squared, plus 5 squared, that is 25, plus 2 times x times 5, that is 10x, minus 25, and it is equals to 100 minus x squared. So in this equation 3, we have 25 minus 25, that is 0. So you can say 25. What is left from equation 3? This side of equation 3 we have x squared plus 10x is equal to 100 minus x squared. Here we will add x squared to this equation, equation 3, and get that according to this equation, equation 3, x squared plus x squared is 2x squared plus 10x equals to 100. Here we will subtract 100 from this equation, equation 3, and so we get that according to equation 3, 2x squared plus 10x minus 100 equals to 0. Here we will divide this equation 3 by 2, and so we get that 2x squared over 2 is x squared, plus 10x over 2 is 5x, minus 100 over 2 is minus 50, and it is equals to 0 over 2 is 0. So in total we found out that according to equation 3, x squared plus 5x minus 50 equals to 0. X squared plus 5x minus 50 equals to 0. So this is a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus C equals to 0. In this general formula, A, B, and C are the coefficients of this quadratic equation, and X is the variable that we are looking for. And we find out the value of X according to the following formula. X equals to minus B plus minus square root of B squared minus 4 times A times C over 2A. In our specific quadratic equation, that is to say x squared plus 5x minus 50 equals to 0, the variable that we are looking for is x. X is actually the radius of this small quarter circle. I'm looking for the radius of this small quarter circle x. And the coefficient A in our specific quadratic equation is equal to 1. The coefficient B equals to 5. And the coefficient C equals to minus 50. So the only thing that is left to do is to put the data of our specific quadratic equation inside this general formula for x. In this way, we find out the value of the values of x, that is the length of this radius of this small quarter circle POS. We do it now and get that x equals to minus b. B is 5, so minus b is minus 5, plus minus square root of b squared. B is 5, so b squared is 5 squared, that is 25, minus 4 times a times c. So it is minus 4 times a is 1, so minus 4 times 1 is minus 4 times c. C is minus 50, so minus 4 times minus 50 is plus 200. So in total, minus 4 times AC is plus 200 divided by 2A. A is 1, so 2A is 2 times 1, that is 2. So in total, we should find out that x equals to minus 5 plus minus square root 25 plus 200 is 225 over 2. So we should find out that x equals to minus 5 plus minus, the square root of 225 is 15 over 2. So here we have two solutions that are possible for x. The first solution for x is that x equals to minus 5 minus 15 over 2. Okay, again, the first solution for x is that x equals to minus 5 minus 15 over 2. Minus 5 minus 15 is minus 20, is minus 20 over 2 is minus 10. So the first solution for x is that x equals to minus 10 in its length. But because of the fact that x is the length of the radius of this quarter circle, x as a length, it must be a positive number. Minus 10 is a negative number, so this solution is the correct solution, and cancel the solution, and we will take into account only the second solution for x. The second solution for x is that x equals to minus 5 plus 15 over 2. Minus 5 plus 15 is 10, and 10 over 2 is 5. So the second solution for x is that x equals to 5 units in its length. That is to say, the length of the radius of this small quarter circle PQS, the length x, is 5 equals to 5 units. The radius of this small quarter circle PQS is equal to 5 units in its length. Our task is to find out the area of this shaded region. So what is the area of this shaded region? From the drawing, it is very easy to see that the area of this shaded region in total, it must be equal to the area of the big quarter circle A or B minus the area of this semicircle minus the area of this small quarter circle PQS. And repeat again. The area of this shaded region in total must be equal to the area of the big quarter circle AOB minus the area of this semicircle minus the area of this small quarter circle PQS. So I write it down. The area that we are looking for, or the area of the shaded region, in total it must be equal to the area of the big quarter circle A or B minus the area of the semicircle minus the area of the small quarter circle PQS. And again, we should find out that the area that we are looking for in this question, that is the area of this shaded region. In total, it must be equal to the area of the big quarter circle A or B minus the area of the semicircle minus the area of this of the small quarter circle PQS. It is very easy to see from the drawing that if you remove from the area of this big quarter circle the area of the semicircle and the area of this quarter circle PQS, what you will get? You will get exactly the shaded area, that is the area that we are looking for in this question. So what is the area of this big quarter circle A or B? The area of the big quarter circle A or B, the radius of the big quarter circle is 10. Therefore, the area must be equal to pi times the radius square over 2. That is to say, it must be equal to pi times 10 square over 2. So it is pi 10 square over 2. The area of the big quarter circle A or B, in total, it is equal to pi times the radius square, that is 10 square over 2. Minus the area of this semicircle. The radius of this semicircle is 5, therefore the area must be equal to pi times the radius square over 2. So that is to say it is pi times 5 square over 2. So the area of the semicircle in total is equal to pi times the radius square, that is 5 square over 2. Minus the area of this small quarter circle PQS. Because of the fact that the radius of this small circle, of this small quarter circle PQS is equal to 5 units in its length, it means that the area of this small quarter circle PQS must be equal to pi times x squared over 4. But x is 5, so it is pi times 5 squared over 4. So in total, we found out that the area of this small quarter circle PQS is equal to pi times 5 squared over 4. Repeat again, the area of the big quarter circle A or B in total equals to pi times the radius square over 4. That is to say, it is pi times the radius square is 10 square over 4. 10 square is 100, so in total in the numerator we have 100 pi over 4. Here in the numerator of this expression we have 5 squared, that is 25, so it is, in total we have 25 pi over 2. In order to overcome factor with this expression, we multiply both the numerator and the denominator of this expression by 2. So 25 pi times 2 is 50 pi, and 2 times 2 is 4. Here we have 5 squared is 25, so in total we have here 25 pi over 4. So in total, we found out that here we take 4 as a common factor out of those first expressions, and we get that 100 pi minus 50 pi is 50 pi, and 50 pi minus 25 pi is 25 pi. So we have in the denominator in total 25 pi over 4. 25 pi over 4 is equal to 19.635 square units in its size. Okay, again, we should find out that the area of this shaded region in total it is equal to either 25 pi over 4 square units in its size, or in terms of numbers, the area of this shaded region is equal to 19.635 square units in its size. So we finished to answer on the first question. In the next step, I will present to you the second question of this lecture, and we saw the second question. Our task in this second question is to find out the size of this shaded area, or the area of this shaded region. So in the drawing you have those two semicircles that intersect with each other at those 2 points, and we know that AB, that is the diameter of this semicircle, is equal to 5 units in itself. And we also know that those two semicircles, that is to say, this is semicircle AB, this is semicircle CB. So those two semicircles AB and CD can go into each other, that is to say, they are identical. And therefore, they must have also the same areas. So, first of all, we will define the area of this shaded region as C. That is to say, the area of the shaded region is equal to C square units in its size, according to our definition. Likewise, we define, first of all, we define the intersection point between the diameter BC from this semicircle and this semicircle. This point is point P. And we define the area of this shape PB, that is actually it is a semicircle, it is a smaller semicircle than the big semicircle CB, so we define the size of this small semicircle PB as B. That is to say, it is equal to B square units in its size according to our definition. And finally, we define the size of this shape BPA or APB as A. That is to say, it is equal to A square units in its size according to our definition. So as I already mentioned before, because of the fact that those two semicircles are identical, they must have also the same areas. That is to say, the area of this semicircle AB must be equal to the area of this semicircle CB. repeat again, because of the fact that those two semicircles, that is to say semicircle AB and semicircle CB, are identical, they have also the same areas. That is to say, the area of semicircle AB is equal to the area of semicircle CB. This is equation 1. So what is the area of this semicircle? Semicircle AB. For the knowledge, it is very easy to see that the semicircle AB consists of those two shapes. So the area of semicircle AB must be equal to the sum of the areas of the two shapes that it consists of. That is to say, the area of this semicircle AB must be equal to the area of this shape, that is A, plus the area of this shape, that is B. So in total, the area of semicircle AB must be equal to A plus B squared in its size. So it is something the area of semicircle AB by A plus B. And the area of semicircle AB is equal to the area of semicircle CB. What is the area of this semicircle? CB. The area of semicircle CB must be equal to the sum of the areas of the two shapes that it consists of. The semicircle CB consists of those two shapes. And therefore, the area of semicircle CB must be equal to the sum of the areas of those two shapes that it consists of. The area of this shape is B. The area of this shape is C. Therefore, the sum of the areas of those two shapes in total it is equal to B plus C, squared in its size. So if we found out in total that the area of semicircle CB equals to B plus C squared in its size. So according to equation 1, we actually found out that A plus B equals to B plus C. Actually, A, B, and C are they are areas. Okay, A is the size of this, the area of this shape, B is the size of the area of this shape, and C is the size of the area of this shaded area. Okay. So, according to equation 1, actually found out that A plus B equals to B plus C. Here we subtract B from this equation, equation 1, and finally get that according to this equation, equation 1, A equals to C. So if we found out that the area of the shaded area, the area of this shaded region, that is the area that we are looking for in this question, is equals to exactly to the area of this shape APB, that is A, because A equals to C. So in order to find out the area of this shaded region, we just have to find out the area of this shape APB, and this will be equal to the area of the shaded region because A equals to C. Okay. So in the next step, we define the center of this semicircle. Semicircle AB is O. AB, the diameter AB of this semicircle equals to 5, and therefore the radius must be equal to 5 over 2. The radius AO of this semicircle is equals to 5 over 2 units in its length. Likewise, the radius OB must be also equal to 5 over 2 units in its length. In the next step, we'll do a construction, that is to say, from point P, we'll go perpendicular on AB. Again, from point P, we'll go perpendicular on side AB. So actually, this angle equals to 90 degrees in its side, and this angle also equals to 90 degrees in its side according to our construction. We define the touching point of the perpendicular from point P and AB. This point is point Q. we define the length of perpendicular PQ as edge. Again, PQ equals to edge units in itself according to our definition. In the next step, we join points P and A together by straight line. By joining points A and P, we get the peripheral angle APB. This is peripheral angle APB. Peripheral angle APB subtend on chord AB. AB is the diameter of this semicircle. So we have peripheral angle APB that subtend on the diameter of this semicircle, and therefore according to rule 7, any peripheral angle that subtend on the diameter of the circle or semicircle must be equal to 90 degrees in size. So according to rule 7, peripheral angle APB must be equal to 90 degrees in size. So repeat quickly on rule 7. According to rule 7, if a peripheral angle subtend on the diameter of the circle or semicircle, then it is equal to 90 degrees in size. In the moment we have a circle, this is peripheral angle ACB that subtend on chord AB. Chord AB is the diameter of the circle, and because of the fact that peripheral angle ACB subtend on the diameter of the circle, it must be equal to 90 degrees in size. Repeat again, according to rule 7, any peripheral angle that subtend on the diameter of the circle or semicircle must be equal to 90 degrees in size. So we can implement rule 7 in our drawing. Because in our drawing we have, this is peripheral angle APB that subtend on AB, that is the diameter of this circle, of this semicircle, and therefore it must be equal to 90 degrees in size according to rule 7. In the next step, we will join points P and O together by straight line. By joining points P and O, consider straight triangle AOP. Straight triangle AOP, this is straight triangle AOP. Straight triangle AOP subtend on chord PA. Again, straight triangle AOP subtend on chord PA. Likewise, peripheral angle ABC, peripheral angle ABC is equal to 15 degrees in size, subtend on the same chord, again, this is peripheral angle ABP. Peripheral angle ABP subtend on the same chord, chord AP. And because of the fact that those two angles are both subtend on the same chord, chord AP, according to rule 13, the size of this straight triangle AOP, it must be twice as large as the size of this straight triangle APP that subtend on the same chord, chord AP. But the size of this peripheral angle ABP is 15 degrees, and therefore the size of this peripheral angle AOP must be equal to 15 times 2, that is 30. So according to rule 13, the size of this straight triangle AOP is equal to 30 degrees. So repeat quickly on rule 13. According to rule 13, a straight triangle is twice as large as the peripheral angle subtended on the same chord. In the drawing, we have a circle. This is straight triangle, and this is peripheral angle ACB that subtend on chord AB, and it is equal to 30 degrees in its size. Likewise, we have straight triangle AOB that subtend on the same chord, chord AB. And because of the fact that those two angles are both subtend on the same chord, chord AB, straight triangle AOB must be twice as large as this peripheral angle ACB. But the size of this peripheral angle ACB is theta, and therefore the size of this straight triangle AOB must be equal to 2 theta. So according to this rule, rule 13, the size of a straight triangle will be twice as large is the size of the peripheral that's subset on the same chord. Okay, so we can implement rule 13 in our drawing. As I already mentioned, we already implemented rule 13 in our drawing, because in our drawing we have peripheral angle ABP is equal to 15 degrees in its size, and it's subset on chord PA. Likewise, we also set angle AOP that's subset on the same chord called AP. And because of the fact that those two angles are both subset on the same chord called AP, the size of this set angle AOP must be twice as large as the size of this peripheral angle ABP that's subset on the same chord called AP. But the size of this peripheral angle ABP is 15, and therefore the size of this set angle AOP must be equal to 15 times 2, that is 30 degrees. Okay. So, in the next step, we will calculate the area of this triangle APB in two different methods. And then we get an equation that says that the area of this triangle APB according to the first method of calculation must be equal to the area of this same triangle APB according to the second method of calculation. So what is there? So I'll copy the right triangle APB in an equation. We find out there are this right triangle APB in two different methods. Hereby PT is aberration of Pythagoras theorem. So actually this is the right triangle APB that I covered from the original drawing. We find out the area of this right triangle APB in the following way. The area of this right triangle APB must be equal to the base AB times the height to the base that is edge over 2. So the area of this right triangle APB equals to the base AB times the height to the base that is edge over 2. And it must be equal to the area of this right triangle APB according to the first method of calculation. The area of this right triangle APB is equal to the base AP times the height to the base PB over 2. Okay. According to the second method of calculation, the area of this right triangle APB is equal to the base PB times the height to the base that is PA over 2. So in total, according to equation 1, we found out that AB times edge over 2 equals to PB times PA over 2. We have 2 on both sides of this equation, so 2 will get cancelled. After we cancel 2, found out of 3. AB is 5, so we substitute AB by 5 and get that 5 times 8 equals to PB times PA. PB times PA. So according to equation 1, we found out that 5H equals to PB times PA. We will continue to focus on this right line APB. So copy right line APB in the new project. We analyze this right line APB. So actually, this is the right line APB, the common from the other line. This right line APB, sinus 15 degrees equals to PA over AB. So I did down. Sinus 15 degrees is equal to PA over AB. AB is 5, so it is PA over 5. So in total, we should find out that sinus 15 degrees is equal to PA over 5. Here we multiply the equation by 5 and finally get that PA equals to 5 times sinus 15 degrees. And again, on the other three, that PA equals to 5 times sinus 15 degrees in its size. We continue to focus on this right line APB. On this right line APB, cosine 15 degrees is equal to PB over AB. So it is PB over AB. AB is 5. So total we found out that cosine 15 degrees is equal to PB over 5. Here we will multiply the equation by 5 and finally we will get that PB is equal to 5 times cosine 15 degrees in its size. And we only found out that PA is equal to 5 times sinus 15 degrees in its size. And according to equation 1, 5H equals to PB times PA. H is equal to PB times PA. Because again, according to equation 1, found out that 5H equals to PB times PA. So 5H equals to PB. We just now found out that PB equals to 5 times cosine 15 degrees. Times PA. Is that I now found out that PA equals to 5 times sinus 15 degrees. So in total, according to equation 1, we should found out that 5H equals to 5 times cosine 15 degrees times 5 times sinus 15 degrees. Here we will divide this equation 1 by 5. And finally we get that according to this equation 1, 5H over 5 is H. So H equals to, here we have to divide it by 5. So 5 over 5 is 1, so we're left only with 1 5. Here we have 2 times 5, so we're left only with 1 5 because we divided the equation by 5, so 1 5 is cancelled. So in total we found out that H equals to 5 times cosine 15 degrees times sinus 15 degrees. And again, according to equation 1, H equals to 5 times cosine 15 degrees times sinus 15 degrees. Here we will use the trigonometric identity that states that 2 times sinus A cosine A is equal to sinus 2A. Here we divide this equation by 2, and finally we get that sinus 2A over 2 is equal to sinus A times cosine A. But again, according to this trigonometric identity, we actually found out that sinus A times cosine A equals to sinus 2A over 2. We use this trigonometric identity here in equation 1. And get that according to equation 1, H equals to 5 cosine 15 degrees times sinus 15 degrees. According to this trigonometric identity, it is equals to sinus 2A over 2. So it is equals to sinus 2 times 15, that is 30 degrees, over 2. So in total we found out that according to this trigonometric identity, cosine 15 degrees times sinus 15 degrees equals to sinus 30 degrees over 2. So in total, according to equation 1, we found out that H equals to 5 over 2 times sinus 30 degrees. So according to equation 1, H equals to 5 over 2 times sinus 30 degrees. Sinus 30 degrees is 1 half. So instead of sinus 30 degrees by 1 half. So in total, we get that H equals to 5 over 2 times 4, that is 4. So in total, we found out that H, the height H is equal to 5 quarters units in its length. H equals to 5 quarters units in its length. So this is the height P cubed is equals to H, and H equals to 5 quarters units in its length. So we already found out that we are looking for this shaded area C. Shaded area equals to C squared inside according to our definition. But we already found out that C equals to A. So the shaded area is this area, that actually the area of this shape PBA, this equals to A. because A equals to C. So we'll find out the size of this shaded area C by finding the value of A. This shape CBA is equals to A squared in size consists of those two shapes. It consists of this shape that is actually sector COA plus this triangle COB. It is very clear that in total the area of this shape ACB will be equal to the area of the first shape that it consists of, that is actually the area of this triangle COB, plus the area of this second shape that it consists of. This is actually the area of this sector COA. Again, in total, the area of this shape ACB is equals to A squared in size. It must be equal to the sum of the areas of those two shapes that it consists of. It consists of the first shape, that is the area of this triangle COB, plus the area of this second shape, that is the area of this sector COA. So, until now, we actually found out that the area that we are looking for in this question, that is the area of this shaded region, it is equals to C, but C equals to A, and therefore we have to find out the size of this shape ACB. Shape ACB consists of two smaller shapes. The first shape, that the big shape PBA consists of is this triangle POB, plus the area of this second shape that it consists of, the area of this sector COA. Repeat again, if you found out that the area of this shaded region, it is equals to C according to our definition, but C equals to A. So we have to find out the size of this shape ACB and PBA. PBA, shape PBA consists of those two smaller shapes. That is to say, it consists of this triangle POB and this sector POA. So the sum of the areas of those two shapes, it is equals to the area of the shape PBA, it is equals to A, and A equals to C. Therefore, by finding the value of this shape, we find out the area of this shaded region, because C equals to A. So to that, we found out that the area of the shaded region, the area that we are looking for, that is the area of the shaded region, equals to the area of triangle POB plus the area of sector AOB. This sector COA. Sector COA. The rounded sign above COA is the sign for a sector. It means sector COA. So, what is a sector? A sector is a portion of a circle. The green shape AOB is a sector. It is like a slice of a pizza. The green shape AOB is a sector. It consists of, it is a portion of this circle. It consists of those two radii and the RKB between them. Again, a sector is a portion of this circle with two radii and RKB between them. It is like a slice of a pizza. And the area of this sector AOB, the green sector AOB, equals to pi r squared. This is the area of the circle that contains the sector. R is the radius of the circle, times the angle between the two radii, that is theta over 360 degrees. The two radii are also defined as the legs of the sector. So in total, the area of this sector, the green sector AOB, equals to pi r squared, times the angle between the legs of the sector, that is theta over 360 degrees. And again, the area of the sector AOB equals to pi r squared times theta over 360 degrees. So, what is the area of sector COA? The area of sector COA equals to pi r squared. That is the radius of the r is the radius of this circle that contains the sector. This is actually 5/2. So it is pi r squared times the angle between the legs of the sector, that is 30 degrees, over 360 degrees. So in total, we found out that the area of this sector COA equals to pi r squared times 30 degrees over 360 degrees, plus the area of this triangle COB. What is the area of this triangle COB? We choose the base as OB. OB is the radius of this semicircle, so the area of this triangle COB equals to the base OB times the height to the base. The height to the base must create 90 degrees with the base OB. And indeed, PQ creates 90 degrees with the base BO. So, and PQ equals to H. So the height is H, because it's creates 90 degrees with the base BO. So it is the base OB times the height H to the base, it creates 90 degrees with the base over 2. So in total, the area of this triangle COB equals to the base BO times the height H over 2. And again, the area of the shaded region is equals to the area of triangle POB, it is equals to the base OB times the height H over 2, plus the area of sector COA equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 30 degrees over 360 degrees. OB is the radius of this semicircle, that is equals to 5/2 times H. H is 5/4 over 2. You have to divide it by 2. Plus the area of sector COA is equals to pi r squared. So it is pi times r squared. The radius of this semicircle R is 5/2. Therefore, r squared is 5/2 squared times 30 degrees over 360 degrees. 30 degrees over 360 degrees is 1/12. So in total, the area of the shaded region is equals to, we have here 5 times 5 is 25. In the denominator, we have 2 times 2 is 4, and 4 times 4 is 16. So it is 25/16, that is the area of triangle POB, 25/16 is correct in size, plus the area of sector COA. So we have here pi times 5/2 squared. 5/2 squared equals to 5 squared, that is 25, over 2 squared, that is 4. And we have to divide it by 12. So in total, the shaded region equals to 25/16 plus 25 pi over 4 times 12 is 48. So in total, we found out that the area of the shaded region is equal to 25/16 plus 25 pi over 48, square root in its size. On terms of numbers, it is equal to 3.2 square root in its size. Students in size. And again, if you want to know that the area that you are looking for this question, that is the area of this shaded region, in total it is equals to 3.2 square unit size. So we finish to answer on the second question. In the next step, I will summarize the lecture. We'll start with the repetition of the solution of the first question, and then we repeat on the solution of this second question. In the first question, our task was to find out the area of this shaded region. So, in the drawing, we have a big quarter circle AOB. Inside this big quarter circle AOB, we have this semicircle and this small quarter circle PQS. Again, our task is to find out the area of this shaded region. So, first of all, it is given as a question that AO equals to 10. That is to say, the radius of this big quarter circle AOB equals to 10 units in its length. So BO is also the radius of this big quarter circle, that equals to 10. BO is also the diameter of this semicircle. So if the diameter of this semicircle equals to 10, it means that the radius must be equal to 5. We define the center of this semicircle, this point as point C. So CO is the radius of this semicircle, equals to 5. Likewise, CB is also the radius of this semicircle, equals to 5 units in its length. We define the touching point between this semicircle and this small quarter circle. This point is point M. So those two shapes, that is to say, this big semicircle and this small quarter circle, touch each other externally at point M. And therefore we can implement the rule 10. Repeat quickly rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects the circles together passes through their touching point. In the drawing, we have those two circles that touch each other externally at point P. The center of this circle is at point O. The center of this circle is at point M. The straight line that connects the circles together is of course the straight line OM. And according to this rule 10, the straight line OM must pass through their touching point, that is point P. Again, the straight line OM must pass through point P, that is their touching point. Or OPM is one straight line. Again, OPM is one straight line according to this rule 10. So we can implement rule 10 in our drawing. Right, for in our drawing, we have an external mass between those two, this circle and this small quarter circle. So we can implement here rule 10. The center of this small quarter circle is at point Q. The center of this big semicircle is at point C. The straight line that connects the circles together is of course the straight line CQ. And this straight line CQ must pass for point M, that is their touching point. Or CMQ is one straight line. Again, CMQ is one straight line according to rule 10. And because of the fact that CMQ is one straight line, it means that CQ in total must be equal to CM plus MQ. So CQ equals to CM. CM is the radius of this semicircle, that is 5, plus MQ. MQ is the radius of this small quarter circle, that equals to X according to our definition. So in total, CQ equals to X plus 5 units in its length. CO is the radius of this semicircle, that equals to 5. This is a right angle because AOB is a quarter circle. Likewise, this is also a right angle because PQS is also a quarter circle. In the next step, I copied the right angle CQO in the new page and implemented on this right angle CQO, or the Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So okay, this is right triangle CQO, this is according to the original drawing. In this right triangle CQO, CQ squared, this is the square of the hypotenuse, equals to CO squared plus QO squared. CQ is x plus 5, therefore CQ squared is x plus 5 squared, and it is equals to CO squared. CO is 5, therefore CO squared is 5 squared, that is 25, plus QO squared. So now we should find out that according to equation 1, x plus 5 squared equals to 25 plus QO squared. Here we will subtract 25 from this equation 1, we subtract 25, and we should find out that x plus 5 squared minus 25 equals to QO squared. Again, according to equation 1, we should find out that QO squared equals to x plus 5 squared minus 25. In the next step, we join points O and P together by side line. Point O is the center of this big quarter circle, A or B. Point P is the point of the big quarter circle itself. Therefore, OP is the radius of this big quarter circle, that equals to 10, according to what is given as the question. And in the next step, a copy the right triangle PQO in the new page and implemented the Pythagoras theorem on this right triangle PQO. So here, this is the right triangle PQO, that is coming from the original drawing. PQ is of course the radius of this small quarter circle, that equals to x according to our definition. So in this triangle POQ, PO squared, that is the square of the hypotenuse, equals to PQ squared plus QO squared. PQ is 10, therefore PQ squared is 10 squared, that is 100. It equals to PQ squared. PQ is x, therefore PQ squared is x squared, plus QO squared. QO is the missing sign, so leave it as it is. So in total, according to equation 2, I should find out that 100 equals to x squared plus QO squared. Here, we subtracted x squared from this equation 2, and find out that according to this equation 2, 100 minus x squared equals to QO squared. QO squared equals to 100 minus x squared. This is according to equation 2. But according to equation 1, we have already found out that QO squared equals to x plus 5 squared minus 25. So we have two different equations for QO squared. Therefore, we created equation 3 that states that QO squared according to equation 1 must be equal to QO squared according to equation 2. QO squared according to equation 1 equals to x plus 5 squared minus 25, and it must be equal to QO squared according to equation 2. QO squared according to equation 2 equals to 100 minus x squared. So in total, according to equation 3, I should find out that x plus 5 squared minus 25 equals to 100 minus x squared. Here we open the brackets of this expression and find out that according to equation 3, x plus 5 squared equals to x squared plus 5 squared, that is 25, plus 2 times x times 5, that is 10x, minus 25. And here it is equals to 100 minus x squared. 25 minus 25 is 0. After we get the 25, in this equation 3, we left only with x squared plus 10x. And on the other side of the equation, we have 100 minus x squared. So total, according to equation 3, we should find out that x squared plus 10x equals to 100 minus x squared. Here we add x squared to this equation 3, and we found out that x squared plus x squared is 2x squared plus 10x equals to 100. Here we subtracted 100 from this equation 3, and we found out that according to this equation 3, 2x squared plus 10x minus 100 equals to 0. Here we divided the equation 3 by 2, and finally found out that 2x over 2 is x squared, plus 10x over 2 is 5x, minus 100 over 2 is minus 15, it is equals to 0 over 2, 0 over 2 is 0. So in total we should find out that x squared plus 5x minus 50 equals to 0. And again we should find out that x squared plus 5x minus 50 equals to 0. So this is a quadratic equation. And the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. This general formula, a, b, and c are the coefficients of this quadratic equation, and x, and x is the variable that we are looking for. And we will find out the value of x according to the following formula. X equals to minus b plus minus 4 to b squared minus 4 times a times c over 2a. In our specific quadratic equation, that is to say x squared plus 5x plus 50 equals to 0, the variable that we are looking for is x. X is the radius of this small quarter circle, PQS. The coefficient a equals to 1, the coefficient b equals to 5, and the coefficient c equals to minus 50. So the only thing that is left to do is to put the data of our specific quadratic equation, this data, in the general formula for x, and this way we find out the value of x, that is the radius of this small quarter circle, PQS. So we did it, we found out that x equals to minus b. B is 5, so minus b is minus 5, plus minus square root of b squared. B is 5, so b squared is 5 squared, that is 25, minus 4 times a times c. So it is minus 4 times a. A is 1, so minus 4 times 1 is minus 4 times c. C is minus 50, so minus 4 times minus 50 is plus 200. So in total, inside the root we have 25 plus 200 over 2a. A is 1, so 2a is 2 times 1, that is 2. So in total we should find out that x equals to minus 5 plus minus 25 plus 200 is 225 over 2. So x equals to 5 plus minus, x equals to minus 5 plus minus, the square root of 225 is 15 over 2. So in total we have here two solutions for x. The first solution for x is that x equals to minus 5 minus 15 over 2, minus 5 minus 15 is minus 20, is minus 20 over 2 is minus 10. But x is a length, it is the length of this, the radius of this small semicircle, of this small quarter circle PQS. So x is a length, it must be a positive number, it can never be equal to minus 10, that is a negative number. So we present the solution for x, and we took into account only the second solution for x, that is x equals to minus 5 plus 15 over 2. Minus 5 plus 15 is 10, and 10 over 2 is 5. So we found out that the length of the radius of this quarter circle PQS, the length of the radius, x is 5. X equals to 5 units in its length. Our test is to find out the size of this area of this shaded region. So what is the area of this shaded region? From the drawing it is easy to see that in total the area of this shaded region must be equal to the area of the big quarter circle AOB minus the area of this semicircle minus the area of this small quarter circle PQS. Repeat again. In total the area of the shaded region must be equal to the area of the big quarter circle AOB minus the area of the semicircle minus the area of the small quarter circle PQS. The radius of this big quarter circle is 10, and therefore the area of this big quarter circle A or B must be equal to pi times the radius squared, that is pi times 10 squared over 4. So in total the area of the big quarter circle A or B equals to pi times 10 squared over 4 minus the area of this semicircle. What is the area of this semicircle? The radius of this semicircle is 5, and therefore the area must be equal to pi times 5 squared over 2. So in total, if you want to know that the area of the semicircle equals to pi times 5 squared over 2 minus the area of this small quarter circle PQS. The area of this small quarter circle PQS must be equal to pi times x squared, and x is 5, so it is pi times 5 squared over 4. So in total, the area of the small quarter circle PQS equals to pi 5 squared over 4. Pi times 5 squared over 4. So here we have 10 squared is 100, so in total in the numerator we have 100 pi over 4. And we have here 5 squared is 25, so in total in the numerator we have 25 pi over 2. Here we multiply both the numerator and the denominator of this expression by 2 in order to have a common factor with the other expression. So 25 times 2 is 50 pi, and 2 times 2 is 4. So in total, this expression after multiplied by 2 is equal to 150 pi over 4. And we have 5 squared is 25, so in total in the numerator we have 25 pi over 4. Here we took 4 as a common factor out of those three expressions. So we have here 100 pi minus 50 pi is 50 pi, and 50 pi minus 25 pi is 25 pi over 4. So in total we found out that the area that we are looking for, that is the area of this shaded region, in total it is equal to either 25 pi over 4 square inches in size, or in terms of numbers, the area of this shaded region is equal to 19.635 square inches in size. So we finish to repeat on the first question, and next step repeat on the solution of the second question. In the second question, our task is to find out the area of this shaded region. So in the drawing we have two semicircles that intersect with each other at those 2 points. You know that AB, that is the diameter of this semicircle, equals to 5 units in length. And those two semicircles are identical, and therefore they must have also the same areas. Again, our task is to find out the size of this shaded region. I repeat again that because of the fact that those two semicircles are identical, they must have also the same areas. That is to say, the area of semicircle AB must be equal to the area of semicircle CB. The area of semicircle AB must be equal to the area of the semicircle CB, because they are identical. What is the area of the semicircle AB? Actually, we define the size of the shaded area as C. This is to say it is equal to C square inches inside according to our definition. We define the size of this shape, this is a small semicircle, as B, and we define the size of this third shape as A. So this is shape APB is equals to A square inches inside according to our definition. So we divided the total area to 3 areas. This is the first area, that is equals to A square inches inside. This is the second area, that is equals to B square inches inside. And this is the third area, that is the shaded area that we are looking for this question, that is equals to C square inches inside. We know that the area of this semicircle AB is equal to the area of this semicircle CB. The area of semicircle AB equals to the area of semicircle CB. What is the area of this semicircle AB? Semicircle AB consists of those two shapes. Therefore, the area of semicircle AB must be equal to the sum of the areas of the two shapes that it consists of. The area of this shape APB is A, the area of this second shape is B, and therefore the sum of the areas of those two shapes is the area of this semicircle AB. This is actually, in total it is equal to A plus B. So the area of semicircle AB equals to A plus B, and it is equal to the area of this semicircle CB. Semicircle CB consists of those two shapes, and therefore the area of semicircle CB must be equal to the sum of the areas of those two shapes that it consists of. That is to say, it must be equal to B plus C. So in total, the area of semicircle CB equals to B plus C. So according to equation 1, we found out that A plus B equals to B plus C. Here we subtract B from this equation, and we found out that according to equation 1, A equals to C. So the area of this shaded region, that is the area that we are looking for, is actually equals to the area of this shape APB. So we'll find out the area of this shape APB and this will be the area of this shaded region because A equals to C. Okay. So join points A and P together by a straight line. We join points P and O together by a straight line. And from point P, we go perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and AB. This point is point Q. We have here, this is periangle APB. Periangle APB subtend on the diameter AB, and the force must be equal to 90 degrees in its size according to rule 7. Again, periangle APB subtend on chord AB, that is the diameter of this semicircle, and therefore it must be equal to 90 degrees in size according to rule 7. In the next step, we calculated the area of this triangle APB by using two different methods. And then we created the equation 1 that said that the area of triangle APB according to the first calculation must be equal to the area of triangle APB according to the second calculation. So I call the triangle APB in a new page. This is the triangle APB that I copied from the original drawing. So the first method of calculation, so the area of this triangle APB is equal to the base AB times the height of the base P times the height of the base AB, that is PQ over 2. We define the length of PQ as such. So in total, according to the first method of calculation, the area of this triangle APB equals to the base AB times the height H over 2. And this must be equal to the area of this same triangle APB according to the second method of calculation. According to the second method of calculation, the area of this triangle APB equals to the base AP times the height PB over 2. This is the base PB times the height PA over 2. So the area of triangle APB according to the first method must be equal to the area of triangle APB according to the second method of calculation. We have 2 on both sides of this equation, so 2 will get cancelled, and finally found out that AB is 5, so substitute AB by 5, so 5H equals to PB times PA. In the next step, I copied the triangle APB in the new page again. We continue to analyze this triangle APB in order to find out the value of AP and PB that are unknown. So this is the triangle APB that I copied again here. This triangle APB, sinus 15 degrees equals to AP over AB. Sinus 15 degrees equals to AP over AB. So it is PA over AB. AB is 5. So in total, we found out that sinus 15 degrees equals to PA over 5. Here we multiply this equation by 5 and finally found out that PA equals to 5 times sinus 15 degrees. Likewise, in this triangle APB, cosine 15 degrees equals to PB over AB. Cosine 15 degrees equals to PB over AB. So it is PB over AB. AB is 5, so substitute AB by 5. So in total, we found out that sinus 15 degrees equals to PB over 5. Here we multiply this equation by 5 and finally found out that PB equals to 5 times cosine 15 degrees in its size. Again, in total, I found out that PB equals to 5 times cosine 15 degrees, while PA equals to 5 times sinus 15 degrees. According to equation 1, we already found out that 5H equals to PB times PA. So 5H equals to PB is 5 times cosine 15 degrees times PA. PA is 5 times sinus 15 degrees. So total, according to equation 1, we actually found out that 5H equals to 5 times cosine 15 degrees times 5 times sinus 15 degrees. Here we divided this equation 1 by 5, so here 5H over 5 is H. If 5 will get cancelled, and we left only with 1 5. So in total, we found out that H equals to 5 times cosine 15 degrees times sinus 15 degrees. We use the trigonometric identity that says that 2 times sinus A cosine A equals to sinus 2A. Here we divided this trigonometric identity by 2 and finally found out that sinus 2A over 2 is equals to sinus A times cosine A. We use this trigonometric identity in order to find out the value of cosine 15 degrees times sin 15 degrees. So according to equation 1, we should find out that h equals to 5, and we have cosine 15 degrees times sin 15 degrees. According to this trigonometric identity, sinus A times cosine A equals to sinus 2A over 2. Therefore, according to this trigonometric identity, cosine 15 degrees times sinus 15 degrees will be equal to sinus 15 degrees times 2 over 2. So in total we get that h equals to 5, and again cosine 15 degrees times sinus 15 degrees equals to sinus 2 times 15, that is 30 degrees over 2. So in total, according to equation 1, we should find out that h equals to 5 times sinus 30 degrees over 2. So h equals to 5 over 2, and sinus 30 degrees is 1/2. So in total, we should find out that h equals to 5 over 2 times 2, that is 4. So in total, we should find out that h equals to 5 quarters units in its length. This is the missing side edge, PQ is equals to h, and h equals to 5 quarters units in its length. And as I mentioned before, the shaded area is equals to this shape APB. This shape APB consists of two smaller shapes. It consists of triangle POB, and it also consists of this sector POA. And therefore, the area of the big shape PBA must be equal to the sum of the areas of those two smaller shapes that it consists of. That is to say, the area of this shape APB in total must be equal to the area of the first shape that it consists of, that is actually the area of sector POB, plus the area of sector AOC, that is the first shape that it consists of, plus the area of the second shape that it consists of, that is actually the area of this triangle POB. The area of the second shape, that is the area of triangle POB. So it is the area of this triangle POB. The area of this triangle POB equals to the base OB times the height to the base PQ, that is edge over 2. So in total, the area of this triangle POB equals to the base OB times the height edge over 2. Again, the area of the triangle POB equals to the base OB times the height edge over 2, plus the area of this sector AOB. And again, that a sector is a portion of a circle enclosed by two radii and the arc between them. And the area of the sector equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector over 360 degrees. And therefore, the area of this sector COA will be equal to pi r squared. R is the radius of this semicircle, this 5 over 2, so it is pi r squared. That is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 30 degrees over 360 degrees. So in total, the area of sector COA equals to pi r squared. This is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 30 degrees over 360 degrees. The radius OB is 5 halves, edge is 5 quarters over 2. R is 5 halves, and therefore r squared is 5 r squared, and 30 degrees over 360 degrees is 1 over 12. So in total, this expression pi r squared times 30 degrees over 360 degrees is equals to pi times 5 quarters squared over 12. Here we have 5 times 5 is 25, 2 times 2 is 4, and 4 times 4 is 16. So in total, this expression equals to 25 over 16. Here we have 5 over 2 squared equals to 5 squared, that is 25, over 2 squared, that is 4. So in total, in the numerator we have 25 pi divided by 4 times 12. So in total, the shaded region equals to 25 over 16, and here we have 25 pi. In the denominator we have 4 times 12, that is 48. So in total, we found out that the area of the shaded region this shaded region, that is the area that we are looking for in this question, is equal to either 25 over 16 plus 25 pi over 48 square units in its size, or in terms of numbers, is equal to 3.2 square units in its size. Okay, thank you very much.